All right, let's talk about K nearest neighbor classification. This would be the first example that we would be going over on non-parametric models. So let's recap on what we mean by parametric and non-parametric. So the model that we have visited before was the linear model, the linear classifier. The linear classifier, or linear models in general, are specified by parameters, by the coefficients. Not all models, however, are parametric, meaning that you will not have to find learnable parameters in every model. So non-parametric means that, or should I say, it does not mean that it will not receive in any way information from the designer, the human that is setting up that model. Most likely, these information would come in forms of hyperparameters. So you would still be setting up the model via most likely those hyperparameters. But the model itself would not learn parameters. So there's no concrete training process because there's no learning of parameters involved. Let's observe here a first example where we have a plot of a 15 nearest neighbor classifier. In this case, as the examples that we have used before, we have two classes, one class that is coded as color-coded as blue, and that's the class 0. And we have another class that is coded as orange, and that's the class 1. As you can tell already, these darker line that you see here, this is definitely not a linear shape. So this is the boundary, the decision boundary that is being created or determined by these 15 nearest neighbor classifier. And you can tell right away that this is obviously a non-linear decision boundary. So how do we define mathematically a K nearest neighbor? One way to think about it is just by following that equation here. So we are, as we have done before, estimating a score. So I'm going to call that score our y hat. And that y hat is essentially going over the y's, the values, the ground truth values, or the target values that you have from the training data, from the available data, for every single sample that belongs to a neighborhood of that input that you are trying to predict. So the input that is being given to that y hat function essentially would determine the points that would be taken into consideration, because the neighborhood of that specific point would determine which points would be part of the summation here. So let's say, for instance, you are trying to predict the input here in where my mouse is hovering over, right? So what I'm going to do is I would essentially identify the neighbors that would be closest, the K nearest neighbors that would be closest to that input that I have specified. So in this example that I have used here, you can tell right away that all my neighbors actually have the actual targets as blue or as 0. So then, because all my neighbors would be carrying the target 0, the prediction in this case would be the value 0. That's not always the case. So if you move, for instance, to a region that is closer to the decision boundary, for instance, in here. So let's say you are given as input a value here very close to the decision boundary. So you could tell just by going over the neighborhood that you would be picking up samples that would belong both to class 0 as well as class 1. So this idea of neighborhood can be calculated precisely by a distance metric, and the simplest example of that calculation of distances would be to just calculate the Euclidean distance between the points. So these visually would represent our understanding of how distant or how close 2 points are. And if you consider any input of that scoring function as a point that lives in your input space, which is what you have here in the slide, you can just create a circle, depending on the number of dimensions, obviously. But if you go with 2 dimensions, you can just create a circle, or more generally, a hypersphere, depending on the number of dimensions that you have. And that hypersphere would essentially be incorporating the closest neighbors for that one given point. You can also see that this is weighted by or normalized by the number of neighbors that we are using. So in this case, where k is 15, which is the example that we have here again, I would be essentially summing up the scores of all my neighbors and then dividing by the number of neighbors that I have taken into consideration. So if I would have 15 neighbors, I would be dividing that sum by 15. As you can expect, anytime that you have the majority of the samples that are part of the neighborhood with the value 1, the prediction would be essentially 1, because that would give a score that is above 0.5. And that's the same criteria that we had before. Anytime that you go above 0.5, you would essentially be classifying as class 1. Anytime that is below 0.5, you would be classifying as class 0. So this idea of majority voting actually is precisely the same idea that equation that we have visited is going over. So the counter example to the previous example that I gave is if the majority of samples that I have is of class 0. So then in this case, I would have a value that is for sure below 0.5 for that scoring function. And then my prediction in this case would be 0, because same thresholding rule applies. Anytime that I go below 0.5, I would be classifying as class 0. So another interesting thing that we can comment on the nearest neighbor, k-nearest neighbor classifier, is that you actually don't have a continuous space when it comes to your scores, the outputs that the y-hat function would be given, right? Because we are discretely going over the k nearest neighbors and then normalizing by or dividing by the number of neighbors that we have, you only have a few possible cases or possible values, right? So more precisely, you have k plus 1 possible different values that can be achieved. And you can see that in that example here. If you have one of the neighbors as being class 1 and you have 15 neighbors, you would be getting the 1/15 y-hat output. If you have 14 neighbors with the ground truth class 1, you would be getting 14/15, and then so on. If we change our k from 15 to 1, what would happen? So what would happen is that instead of taking into consideration the 15 closest samples that we have from our training data, I would be considering only the single one that is the closest to my input value. In some cases, you would have points that are equally distant. So in this case, you just need to make a decision, kind of similarly how you do when you have a point that would be sitting precisely on the decision boundary. this means that there's no really any meaningful criteria that you can use to differentiate between one point and another. So visually, if we would observe the outputs of our scoring function, you would see, because these are discrete values, right? So you would see these as steps. So this is not a score that would vary continuously. Instead, because I only have a few possible values, I only have k+1 possible outputs of my scoring function. So you see that essentially as different planes or shelves that could be in your space that is comprised both by the input and the output, which would be your prediction, your score. And you see another example here where we see those different levels that can happen. For k being equals to 1, you only have 2 levels because you have k+1 levels, right? And then depending on how many levels you have, how many k you choose, you would have k+1 different heights or different shelf levels in that visualization that we have here. So what if we want to compare different models, choosing different k values, right? And also compare against our previous model that we have seen, the linear model. Which of those models would we say that is the best one? So in the left-hand side here, we have our linear model, and you see that because the decision boundary is a straight line. In the middle, you have the 15 nearest neighbor classifier. That was the first example that we have visited in this lecture. So you see that you have a very nonlinear decision boundary here. And then finally, on the right-hand side, you have the 1 nearest neighbor classifier. So you see that now you have a very distinct way to classify. You see a lot of variation depending on the region that you are at, and you also see not only 2 distinct regions, but you actually see a lot of regions that would be giving the prediction of 0, and a lot of regions that would be giving the prediction of 1, and so on. And that's something very typical to see when you have when you use a k that is a small value, such as k equals to 1. So back to my question, what or which of those would be the best one? Think about that for a bit. So the sort of not very precise answer to that question is that this really depends. And depends on what? It depends on the data. So the data that you see coming from your training data set is a data that is supposed to represent the actual distribution of the phenomena that is representing. That can be true, or that can be not true, and there are varying degrees to that statement as well. So how can you tell how well your data actually is representing that actual distribution? You can't, right? So the one thing that you can evaluate perhaps would be how well that data was generated, and then make assumptions in terms of how much you can trust that data. So another thing that is interesting to comment, or a different way to think about this question is every time that you do a measurement, that measurement carries an implicit error. That implicit error is usually referred to as a noise. There's no way to fully remove the noise from measurements. So you can try to be as precise as possible, but there's always noise in any data set that would be used. So the noise is something that also needs to be taken into consideration, because since it's part of the data, it's part of the values that the models will be trained on, to some degree, it prohibits the model from having a perfect view of the actual phenomena that the data is representing. So that concludes our lecture on non-parametric models. We have visited the KNN classifier, and we have briefly compared against our previously seen model, an example of a parametric classifier, the linear classifier that we have seen. And I will see you on the next video.